Okay, North Tahoe Lakers, young physics students, another video installment here. This one we're going to focus on a new term to us. To most of us, we've never heard the word entropy before we've entered into a physics classroom. We're going to discuss what that means and what does it have to do with a profound law, one of my favorite laws in all of physics, the second law of thermodynamics. Things you're going to want to focus on in this lesson in order to answer the questions on the homework check. What's the definition of entropy? How do you determine if a system has high or low entropy? How is a system's efficiency affected by entropy? And what are some of the ways the second law of thermodynamics is stated? It's stated a number of different ways. So first things first, what is the definition of entropy? Entropy is a measure of a system's disorder. So if something is really neat and ordered, we'd say it has a very low entropy, a low disorder. If something's really, really messy, has a lot of disorder, we'd say that that's a high entropy. That system's in a high entropy state. Now, how do you rank, though? That's something that's kind of soft in physics. How do you rank disorder? How do you say one system is more ordered than another? We're going to take a look at some analogies and figure it out. A simple analogy might be a bedroom. Like we have a really clean bedroom here. We'd say that that's a low entropy bedroom. It's pretty ordered. Everything's in its right place. There's not a lot of messiness in this case. This bedroom, of course, maybe some of ours looks more like this. We'd say that this, in terms of physics, is a high entropy bedroom. How do we rank those? Well, visually, it's pretty obvious. But what are we going to look for? A low entropy state, we're going to be able to notice a small change very easily. A high entropy state, a small change will be harder to notice. So we're going to run a test here, see if you get the idea. So let's go ahead and run this test. Here's a low entropy state, and what we've said is if we make a change, a small change, it should be pretty noticeable. So study that picture. Now I want you to close your eyes. I'm going to make a change. I'll tell you when to open them. Don't cheat. When I tell you to open them, see if you can notice the change. So go ahead and close your eyes right now, and again, I'll tell you when to open them. So I've made a change. Go ahead and open your eyes and see if you notice it. Oh my God, what a slob. This person put a sock on the floor. That change was pretty noticeable because the system was at a low entropy state. Something's out of order, we definitely know right away. Let's check the next system, see if we can find a change in this one. So again, higher entropy, a small change should be harder to notice. So take a look, study that, and close your eyes. I'll tell you when to open them. See if you can notice the change this time and how quickly it takes you to notice the change. Okay, go ahead and open your eyes. Do you notice the change? If you notice it, how much easier or harder is it to notice the change for the last one? If you didn't notice it, see if we can find it here. What I did here is I had an extra sock and I removed it. So that small change is probably a lot harder to notice because this room has so high of a level of entropy. Okay, so it's one thing to talk about messy bedrooms, but what about an actual physical system? So this diagram, we have a gas, which are represented by these little guys there. Those are gas molecules or atoms, and they're moving. They have some amount of kinetic energy, and we'll make it simple. Each one of them has 10 joules of kinetic energy. They're in a piston, so this is kind of a hard thing to describe. The piston, if those gas molecules collide correctly with the piston head, the piston is moved in that direction. It would do work by pushing a force, exerting a force, and pushing it some distance in there. So let's first of all, talk about its entropy. Is this a high or a low entropy system? Well, if I make a change to it, is it easy to notice? And one way we can think about all of those particles are moving in different directions. If I make a change, if I change just one of these, move that one in that direction, it's not that easy to notice. So this is a high entropy system. Let's go back to what we learned about efficiency then in the system. Remember, if we loosely talk about efficiency as what you get divided by what you pay, For an engine that we're trying to design here, what we want is work, right? And what we pay with the total amount of energy that's used, in this case thermal energy. So let's take a look at how much energy that we have. We've got 12 particles, each has 10 joules of kinetic energy, so the total thermal energy is 120 joules. Of that, only the particles that are going to actually collide with the piston and move it are going to do useful work for us. So when I look at this, I only see 3 particles, so only 30 joules of work can be done. So that means our efficiency of that 120 joules of energy that was available to us, only 25% of it, or 0.25, was able to do work. We have a 25% efficiency. That's relatively low compared to what we're going to look at next. So high entropy is associated with low efficiency. So let's take a look at this one. Same total amount of energy involved, 12 particles, each with 10 joules of kinetic energy. But this has a much lower entropy. You can see that this system is much more ordered rather. If I make a small change, say move this one or change this one's direction, that's pretty noticeable. All of them went to predominantly being pointing towards the right, actually doing useful work. You change one and it's pretty noticeable when there's a small change. So this is a low entropy system in this case. Take a look at the efficiency in this case. Again, we still have 120 joules of total energy. Each one of those particles has 10 joules of kinetic energy. And when I look here, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 joule or 10 particles that are moving in the direction that are going to do useful work, that are actually going to push the piston in that direction. So that's 100 joules of work that we're getting out, and we're only putting in 120 joules of energy. So that gives us an efficiency then of 0.83 or 83%. 83% of the energy that we put into the system does useful work for us. So the opposite is true for a low entropy system. Low entropy is associated with high efficiency. Okay. Now what we're going to spend time in class discussing, what's the significance of this? Entropy is tied into the second law of thermodynamics, and as I said before, it's pretty profound in what it actually has to say about ultimately how the universe unfolds. But the second law is stated a lot of different ways. One of the ways, as I said, is nature spontaneously moves towards a state of more disorder, higher entropy. We'll take a lab that tells us why is that. Why does that happen? Number two, another way we can talk about 100% efficient engine is impossible. We will never get all of our thermal energy to do work. We're always going to lose some of that energy to the outside. Some heat must be lost or exhausted to the surroundings. We'll take a look at why that has to happen. You might already be able to figure it out by looking at those piston diagrams. 4, natural systems tend towards equilibrium and efficiency declines. And 5, heat spontaneously flows from hot to cold. All right, so that's it for entropy and the second law. We're going to explore what this means in class. Go ahead and make sure you have the notes and do the homework check.